Hello everyone. Welcome to Chapter 10, Chemical Bonding. And this chapter is where things are really going to start to come together. All of the skills that you have learned in the previous chapters are going to start to come together to help form a picture of what the structure and shape of certain molecules are. Now, in a normal semester, this is where I usually get to show pictures from my master's thesis that dealt with structure of a particular macromolecule in the cell and how that structure, how those chemical bonds helped predict what the function was of that molecule. I'm not going to share those now just because I know we have other things we need to do, but this idea of chemical bonding predicting structure of a molecule is going to be important in this course. And structure often dictates function. So the structure that we are going to be talking about for the smaller molecules of this chapter, the structure is going to be dictated via bonds that are formed between atoms. And remember that bonds are formed by electrons. And these bonds, when they are shared by atoms in the same space, those attachments create a geometry. What this chapter is going to focus on are two different bonding theories, or two different models that will help us predict the shape of certain molecules. Those two theories are called Lewis structure theory and VSEPR theory, which is a fancy abbreviation for valence shell electron pair repulsion. Okay. We will talk much more about VSEPR in subsequent videos, but what this little vignette is going to focus on is just some of the nuts and bolts about Lewis structure theory. What is a Lewis dot? What is a Lewis structure, and how do you draw a Lewis dot structure for a single atom, for a single element? So Lewis dot structures are based from Lewis theory. They get their name from the scientist Gilbert Lewis. That's his claim to fame. If you go on in chemistry, you will probably learn about Lewis acids and bases, named from the same individual. What you guys need to know about Gilbert Lewis and his Lewis theory is about Lewis dot structures. And in Lewis dot structures for elements, we are only concerned actually with representing valence electrons. Valence electrons are the electrons associated with an atom in the highest principal quantum number. We talked about principal quantum numbers in the previous chapter. Okay. And we show those valence electrons for a particular element as dots. Okay. So if I was to do the Lewis dot structure for hydrogen, I would write down my symbol for hydrogen. And I would see from my periodic table that hydrogen's 1s1, it only has one valence electron. And so that valence electron will be shown or illustrated as a dot. Okay? So Lewis dot structures use element symbols and dots as valence electrons. We don't show all the electrons, just the valence ones. So we talked about in the previous chapter that valence electrons, those are the electrons associated with the highest principal quantum number. That's true. But a quick and dirty way to determine the number of valence electrons for an element, specifically any main group element, that means elements in groups 1 through 8, skipping the transition metals, those middle D elements. But the number of valence electrons for any main group element is equal to the group number of that element. The one exception is helium. We usually put helium over by the noble gases, but helium, its electron configuration is just 1s2, so helium just has 2 valence electrons. Okay. So you can, aside from helium, you can use the group number that's associated with an element from the periodic table to determine the number of valence electrons in that element. For example, and we're going to do many examples, let's say I wanted to write the Lewis dot structure for oxygen. If you look at your periodic table, you see that oxygen is in group 6. So I already know that it has 6 valence electrons. So I could use the group number to determine that. I could have also, if I wanted to, write the electron configuration, and I would see that those electrons that are associated with the highest principal quantum number, 4 plus 2, that's 6. So to do my Lewis dot structure for oxygen, I would write down the symbol for oxygen and place 6 valence electron, or place 6 electrons around that oxygen, just like this. Now notice when placing the electrons, you can see here that I don't have all 6 electrons on one side of the oxygen and the other side of the oxygen is empty. The order in which you place electrons around the element is important. Specifically, think about when you write the element symbol, it could be for oxygen or whatever element you're dealing with. You need to, when you place those valence electrons, you first need to place them singly, and then only when you are done placing them around that element singly do you double up. It's sort of like the Pauli exclusion principle. In the Pauli exclusion principle, and also with Hund's rule, you didn't pair up electrons in the same orbital until you only had to. Same thing with valence electrons. So if I was to do the electron or the Lewis dot structure for oxygen, I would do my O, and now I need to place 6 electrons. I need to place them singly first, so I'm going to do 1, 2, 3, 4. I have placed 4 of my 6 valence electrons. I've got 2 more. I don't have any other size to place them on. So now I need to start pairing them up until I place my final 2 electrons. So 5, 6. So that would be my Lewis dot structure for oxygen. So when you place electrons, valence electrons around the element, you can think about that element as having 4 sides to it, kind of like a square. And you could only place electrons around that side first singly and then doubly. So basically what I said at the previous slide is said here. Each dot is 1 valence electron. When you place them around the atom, do singly first and then pair them. Helium is the exception. Helium is the exception. So I have here phosphorus. Here's the Lewis dot structure for phosphorus, but to double check yourself, you write the symbol for phosphorus, and then how did I know that there was 5 valence electrons around it? Phosphorus is in group 5, so I need to place 5 valence electrons. So I do singly first, 1, 2, 3, 4, and then I place that 5th one. Okay, so note that it doesn't matter that these 2 electrons are on top for this Lewis dot structure and they're on the side here. As long as you place them singly first and then pair them, you will have a proper Lewis dot structure. So both of these would be correct for phosphorus. What would not be correct is something like this, where I have 2 pairs of electrons together and nothing on the side here. That would not be correct. So that's phosphorus, the one exception of helium. Here are some more representative examples of Lewis dot structures. Specifically, these examples are taken from group 1 through 8 on the periodic table. So this is a representative of group 1, lithium, 2, 3, 4, 5, 6, 7, and 8. So that kind of illustrates that you can use the group number for representative elements as the number of valence electrons that you need to place around that element. Then one more important point about this slide is this new rule called the Octet Rule. So if you remember when we talked about properties of atoms, we said something to the effect that those noble gases, those elements that are in group 8, we said they were very stable and very unreactive. Because they are very stable and unreactive, elements like to have the same number of valence electrons as their closest noble gas. So that leads to something that's called the Octet Rule. Octet meaning 8. And there's sort of two parts to it. The first being that atoms with 8 valence electrons are really stable. So that's why a lot of those noble gases don't react very readily. But the other part of the Octet Rule is that for all the other elements, for all the other representative elements, in chemical bonding, these guys, meaning elements in group 1 through 7, they want to beg, borrow, steal, do whatever they can, transfer or share electrons so that they have outer shells of 8 electrons. So that is called the Octet Rule. I'll give one example and then I'll stop this video. If you remember all the elements in group 7, like fluorine, chlorine, bromine, iodide, we said that in an ionic compound, they like to have a charge of -1. They want to gain 1 electron when in an ionic compound. So now hopefully you can see why, because if that fluorine or chlorine or bromine, that element in group 7, gains an electron, how many valence electrons will that element have? It will then have 8 and satisfy the Octet Rule. So the Octet Rule is what is used to predict charges of elements in ionic compounds. And this Octet Rule is going to be really important once we start doing Lewis dot structures, not really of atoms, but of overall molecules. So in the next little video, we're going to do some more examples of Lewis dot structures for individual elements, and then we will move on to Lewis dot structures of slightly larger compounds.